Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very happy to have a person we are interviewing for a postdoc in theory/crypto. And this is Yael Talman-Kalai. She's going to be talking about the limits of obfuscation.
Thanks, Jennifer. Okay, so I'm going to be talking about the limits of obfuscation, and this is joint work with my PhD advisor, Shafi Goldwasser. Okay, so, forgot I have this. Oh, sure. Hi. Okay, so I'm going to be talking about code obfuscation. And so what is it? So to obfuscate means to take a program and to intentionally make it unintelligible, but to preserve its functionality. So what do we mean? You take some program. So an obfuscator takes some program P and obfuscates it and generates an obfuscated program where this program is mixed, okay? It's garbled, it's supposed to be totally unintelligible, okay? And so the goal is to change the program so it still has exactly the same input-output behavior, but now it's impossible to understand the internals of the program, okay? So, typically when people code, they want to do exactly the opposite, right? To make the program actually so people be able to understand what's going on. And so here, it's kind of the opposite style. We want to make it totally unintelligible. And why do we want to do such a thing? So there are many applications to code obfuscation. And let me give you just a few applications in the real world where they use obfuscation. So first, consider the example of code of a copy protection or of a licensing scheme. So let's suppose you want to sell software to somebody, but you want to make sure that that only legitimate users will use it. Okay, only someone who bought the software. So you don't just want to give. So what you do, you first test if the user is legitimate. And there are several ways to test that. I don't want to go into that part. But one test, if the user is not legitimate, then exit. Okay, don't run the program. Else, run the program. Okay, so that's the type of thing you want to make sure you want to do in order to make sure that only legitimate users use this program. But if you just sell it this way, then they'll just erase the lines of the program that the if-else part, right? So in order to avoid this attack, what you do, you obfuscate the program. So you leave the if-else statement, but you obfuscate in a way that they won't be able to take it out. Okay, so this is one example. There are several others examples. So for example, spammers use obfuscation to conceal the fact that their code spawns pop-ups. Okay, and it's also used for watermarking. I don't want to get into details exactly, but it's also used, in general, it's used to prevent reverse engineering of the program. So in particular by competitors, okay, you don't want competitors to be able to reverse engineer and learn the internals of your program, or by hackers, for example, for games, okay, hackers typically try to crack games, so they look into the internals of the program, try to crack it, so you want to obfuscate, so not to allow them to do that. So there are several obfuscation, and even there are several off-the-shelf obfuscators that exist, and so it's a very useful concept. In cryptography, for us cryptographers, actually obfuscation is a real dream. So there's many things you can do in cryptography, and let me talk about specifically one example that I'm going to talk about it's going to come back throughout the talk. So consider the example of cryptographic delegation, okay, or in particular, signature delegation. Okay, so what do we mean by signature delegation? So just a little background about crypto. So usually we assume in cryptography that each user is associated with a pair of keys. okay, a secret key and a public key. And using these keys, so let's take a user Alice. Using these keys, Alice can sign messages. Okay, so what do we mean? Alice can take any message M, and there exists some algorithm, okay, a sign algorithm that depends on her signing key, SK, and outputs some signature, okay, such that this signature can be verified by anyone given Alice's public key. Okay, so this is something that, basic cryptographic primitive, okay, signature schemes. Now, let's assume Alice wants to, so she has a signature scheme like that. She can sign messages, but let's assume now Alice wants to allow her assistant, Bob, to sign messages on behalf of her, but only messages that were signed, let's say, on October 2005. Okay, so only messages with the date October 2005. How can she do that? So the first idea that comes into mind, okay, just send him the secret key. Okay, he has a secret key and can now sign anything. But that may be too much information, because maybe Alice only wants him to be able to sign messages with the date October 2005. And she doesn't want to allow him to, to know her secret key. So if you have obfuscation, this can be achieved. How? What she will do, she will construct a program that on input a message M, it will check whether the date on the message is October 2005, and only if so, she will output, the program will output the signature of the message. Okay, so she creates this program, and what she will do, now she doesn't want to just give it in the clear, because then, like I said, Bob can look and maybe find the secret key from it. So what she will do, she will obfuscate it. Okay, she will obfuscate it away, so it'll be totally unintelligible, and all Bob can do is, just input a message and hope to get a signature if the date is correct. It's October 2005. So this is one example, and like I said, I'm going to go back to this one. By the way, if you have any questions, please stop me at any time during the talk, okay? Because I'm not sure, I know different people here have different backgrounds, so let me know if I'm going too slow or too faster.
There's a spectrum of background, so I think you're perfect.
Okay. Okay, so this is one example. And then there are several other examples that I don't want to go into detail, but it can be used, for example, to transform any secret key cryptographic primitive into a public key one. And this is usually it's useful because secret key primitives are usually very efficient, very easy to construct. Public key ones are typically much less efficient and harder to construct. So you would like to have, to be able to transform secret key to public key one. So using obfuscation, you can do that. You can compute unencrypted data, solve several access control problems, and essentially many cryptographic tasks could be achieved by writing a simple program, obfuscating it, and if obfuscators exist. So we really would like to construct good obfuscators, and the question is, can we? Okay, do they exist? So what's known about obfuscation? So very few, not much is known, unfortunately. So on the negative side, Barak et al. Showed that actually I said I should say all the names, I kind of practice. So because everybody says Barak et al. And people get upset because there's so many authors. So it's actually Barak, Goldreich, Impagliazzo, Rudich, Sahai, Vadan, and Yang. Okay, so they showed, from now it's going to be Barak et al. So they showed that there exist functions that cannot be obfuscated. Okay, but their functions were a little weird looking, and essentially their idea, and this is very loosely speaking, their function is essentially the following: it outputs some secret bit B, only if it's fed itself a description of itself as input. So it's a style of recursive function that if it's fed itself, then it outputs a secret bit B. That's very loosely speaking the idea of their function that they showed that cannot be obfuscated. So that's all that's known about that was known about negative results. What about positive results? So on the positive side, also very little is known, and essentially the only thing is known that very simple functions cannot be obfuscated. In particular, Canetti and Wee, double E, showed that password functions are obfuscatable, and password functions are are very simple functions that they output 1 if and only if they're fed the password as input. Okay, so given the password, they output 1, otherwise they output 0. So that's a password function, also known as point functions. So these cannot be obfuscated. And recently, Dodis and Smith showed that also approximate password functions cannot be obfuscated, and approximate, can be. Sorry. Yeah, these are positive results. Sorry. So password can be obfuscated, and also approximate password can be obfuscated, where approximate password, it outputs 1 if the input is close to the password. Okay, and in there we're close meaning Hamming distance. So that's more or less all that's known about about obfuscation. And what still was left open from these works is, are most functions that we care about, are they obfuscatable or not? Okay, so we know there exists kind of weird-looking functions that are not, very simple functions that are obfuscatable, but most of the functions that we would like to obfuscate, can we or can we not? Okay, so that was not known, and today I'm going to describe a work that kind of gives evidence to the fact that maybe most functions are actually not obfuscatable. Okay, and what do I mean? So let me now give the outline. So this was only a brief introduction for obfuscation, and let me now describe so what's going to be the outline of the rest of this talk. So first I'm going to define the notion of obfuscation, which was actually done by Barak et al. In their work. So I'm going to review their definition, and then I'm going to describe our results, which essentially say that there are many natural classes of functions that cannot be obfuscated. And we do this via an attack which is based on multiple obfuscations. And I'll explain what I mean shortly. So after we describe our result, I'm just going to give some conclusions and talk a little bit about future work. So any questions up to now? Okay, so let me start with the definition of obfuscation. So recall, like I said, and for those who just came late, so what is an obfuscator? It takes some program, and it mixes it, garbles it, creates another program, an obfuscated program, such that this program has the same input-output behavior, but now should be unintelligible. Okay? Now, how did they formalize unintelligible? So the way they did it, they said, well, the obfuscation should be essentially equivalent to black box access to the function. So in other words, all you can do with this obfuscated program can be run it. So all you can do is feed it inputs and get outputs. Other than that, you can't do anything else with the program. So that's the intuition behind their definition.
So you, for example, not allowed to use it. It's a random number generator with some intermediate output.
Exactly. You can't use it. Right. Exactly. Yeah. So more or less, let me go into the formal definition. And so what was their formal definition? So an obfuscator. So they define an obfuscator for a class of programs P. Okay, so it's not just one program, because with one program, you can just look into and learn anything. So they took a class of programs P, and so an obfuscator for this class takes as input a program in the class and produces an obfuscated version of this program, and it should satisfy two properties. So the first one is it should preserve its functionality. In other words, the program P in the program obfuscation of P should have the same input-output behavior. And the second property is what they call the virtual black box property. Okay? And essentially, the property says that whatever deterministic predicate can be computed from the obfuscated program can also be computed merely from black box access to this program with essentially the same probability. Okay? So whatever predicate you can compute given the obfuscation, you can compute with only black box access to the program. Okay, and just formally, the way the more formal definition is that they say for every adversary that gets an obfuscated version, there exists an adversary with only black box access, such that for every program in the family and for every predicate, the probability that the adversary A outputs succeeds in computing this predicate is essentially the same as the probability that S succeeds in outputting this predicate, where S only has black box access, and it should have the size of the program.
And essentially will depend on what here? Will depend on pi, or it will depend on?
You mean what the probability? What it's over?
Yeah. The probabilities differ. How much they differ by depends on.
Oh, okay.
What
So
here.
okay. So the you mean what does equivalent mean? Okay.
Yeah.
So good. So the adversary in the when I say every adversary, there is another adversary. Every I'm assuming that everybody in my world is, let's say, probabilistic polynomial time machines or probabilistic circuits, polynomial time circuit, polynomial size circuits. Okay, so everybody is bounded, and when essentially means the same except with negligible probability. So in other words, for every
Negligible depending on.
negative depending on the size of the program.
Okay, fine.
Yeah.
So epsilon going to 0 as the size of the program goes to infinity?
Exactly. Epsilon goes to 0 as the size of the program goes to, well, okay, so it's the, okay.
For every epsilon.
Yeah, exactly. Think of the program as getting inputs a specific size. So think about them as circuits. Or so if the program takes inputs of size n, then this will be negligible in n. So it's the programs I'm considering are also polynomial size programs. So everything. So the way it's really formalized mathematically is if the program takes input size n, this should be negligible in n. Okay. But so there's all this math, but all these notations, I should say. But the main thing that people should get from this, the main point that we need for the rest of the talk is, the bottom line is an obfuscator should not leak any information, not even a single bit, okay? More than what you can do with black box, okay? So that's the way they defined obfuscation.
Regarding the definition, could you unobfuscate this one? And so you could think about relaxing the preserving functionality part to saying that they're equal with high probability or something.
Right. So actually, Barak et al. Also defined. So this is very strong. What, they need to be exactly the same on every input? So this definition was actually relaxed a little bit. Showed, okay, what if you want it to be almost the same? So with very high probability the same. Their negative results still hold, and our negative results still hold, with respect to the little weakening that you just suggested. Okay. So like I said, the bottom line is the obfuscator should not leak any information, not even a single bit. Okay, that was their definition. Okay, so what is our results? What we show is that there are many natural classes of functions that you cannot obfuscate, but with respect to auxiliary input. What do I mean by auxiliary input? So two things. First, we're going to show that the previous definition that they suggested, even though it seems very strong in the sense that all you can do, everything you can learn, all you can learn is black box access, which is very strong. Still, in other dimensions, it's not strong enough. Okay, so in particular, we show that it's not robust against what we call a multiple obfuscation attack, and I'm going to explain what it is in a second. And so this led us to the conclusion that we should consider auxiliary input. And then we show that many programs of interest are not obfuscatable when you consider the auxiliary input. Okay? So let me first explain why we need to consider auxiliary input, and in one sense, their definition is not strong enough. Okay, so let's go back to our example of signature delegation. Okay, so we have our user Alice with her secret key and public key, and there's her assistant Bob, and she wants to allow him to sign messages only with the date October 2005. And like we said, this can be achieved by obfuscating the program that signs only messages that are with the date October 2005. Okay, so she sends this to Bob. But what if 1 month later, she also wants to allow Bob to sign messages with the date November 2005? So he says, okay, so again, she creates this program, she obfuscates it, and sends it over to Bob. But now, Bob has two obfuscations. I mean, it may be the case that even though each one of them is equivalent to a black box access, maybe together he can somehow find the secret key. Okay? And this was not, this may happen according to their definition. This was not ruled out by their definition. So that, we thought, that's a problem. Okay. Some may come and say, well, okay, so maybe it's not really a problem. Maybe we can just, okay, it's a good obfuscation, but just advise Alice, don't use it more than once. Okay? So, okay, that's one remedy to the problem. However, so it's problematic in two respects. First of all, okay, so Alice can't use anything that has to do with her secret key, and, it's still problematic because maybe she wants to still use her secret key in other...
No, wait, are you saying that you were using the same obfuscation function twice, or are you using another node for the class?
The problem with this, the problem is much broader, okay, it's not, but it's essentially the problem is she's using the same secret key. It can be a different obfuscation.
It can be a different
Totally to the obfuscation.
The same secret.
Exactly.
Okay.
Totally different, independent obfuscation, but maybe she uses a secret key another, and maybe, okay. But it's good that you're asking because what we show is actually something quite surprising and much stronger. So let's say you advise Alice, don't use your secret key for anything else, don't obfuscate twice with the same secret key, or don't, just use it for this. Okay, it's a little problematic because maybe she does want to use it again, but fine. Still, this is not enough. So what we show, and this is what I think is kind of surprising by this work, we show that there may exist a totally independent person, Carol, okay, that doesn't even know Alice, and has totally independent pairs of secret key and public key. And she also knows Bob and wants to send Bob some obfuscated circuit of a total obfuscated program of a totally different independent function, okay? And what we show is that from these two functions, she can compute, Bob can find some secret that maybe he could not have computed given black box access
So
to the
it's
functions.
not necessarily the secret key of either of them.
Exactly.
But it is information.
Exactly. So essentially what we show that even if Bob gets totally independent, some auxiliary information, he may learn something. Yes.
But can't Bob produce the same information Carol has produced on his own?
Good. So that's the first surprising thing. Like, wait, that can't be. Something's wrong. Probably we have a mistake here because Bob can produce it on his own. He can produce it on his own. But what we want to show, the point is, we want to show, there exists something that you can do with. So, what's the definition? How do we define a bad obfuscation? A bad obfuscator. A bad obfuscator is such that given these two things, you can compute something that you could not compute if this was black box. Okay. Now, if Bob would, if the adversary would construct this on his own, then given black box to this, he would be able to learn the secret. The reason he cannot learn the secret, the adversary, is because this is obfuscated. So the adversary that's given black box access. Okay, I mean, in our example, I'll go into
I'm missing your answer to the question, so maybe you're giving it, but I'm missing it. I understood the question. but
Yeah.
I'm
Okay.
not
So
getting the
good.
answer.
Okay. So the question was, why can't the adversary who's trying to learn something? Why does he need this piece of information? He will construct it himself. So the point is, if he could construct it, he can construct it himself. That's true. But then the other adversary, which we denoted by S, or is also noted by a simulator, but never mind, the other adversary, if he would construct this obfuscation by himself, then he would be able to learn the secret. So this secret, the idea is this secret cannot be learned by someone with black box access to this and an obfuscation of this function. Okay? With the function in the clear, he can learn the secret S.
In other words, the secret could, for example, does the secret S has to be a secret S about
Yes.
the brunette, or could it be one
Yeah.
about the blonde?
So the secret, in our example, the secret S is a function of both this secret key and of secret key and secret key prime.
Right, so it could, for example, just be PK prime.
Well, that's not a secret, but if you can't learn it. Okay, yeah, exactly.
So in other words, this that would contradict, or that's
Exactly.
You would just learn something. If you knew the blonde in and out, you would not learn anything.
Exactly. That's exactly. Exactly. So, for example, I mean, this is not the case in our example, but for example, just to demonstrate,
Not his native.
S can be secret key prime, okay? And if S is secret key prime, if adversary can simulate this, can construct this by himself, he learns secret key prime, okay?
For
So
example, it could be the XOR of both secret keys. That would be something.
exactly. And actually, now I'm going to show you exactly what it is. So, okay. And I just want to say something before this. So it seems like some magic is going on here, okay? So let me tell you where this S that I'm going to learn, which I'm going to show you shortly, is actually, it's not necessarily interesting piece of information. Okay, it's not like the secret key, or it's not necessarily something that you would want to learn. But nevertheless, it's some bit of information that you cannot learn from black box access. Okay, so in some sense, you can do it's a contrived piece of information. I mean, it's not necessarily interesting piece of information, but nevertheless is a bit of information that you cannot learn. And I'm going to go back to this point and towards the end of the talk and explain a little bit, elaborate on this point. Okay?
So I guess near the end of the talk, what you're going to say is that maybe you should somehow try to define something so that you would allow really useless information. But I don't know.
Or exactly. So that's one direction. But I'm going to actually talk a little.
Okay.
Yeah. Well,
Good.
yeah. There's going to be more than that.
If I had access to good randomness, and I would say the obfuscator takes as input both the program to obfuscate and a random
Exactly.
number, and each time I run it, I would use a new random number.
Yeah, that's good. Right. So an obfuscator, essentially, for an obfuscator to exist, it has to be a randomized. It has to have some randomness in it. Okay, it can't be deterministic, because if it's deterministic, you can also always, given the obfuscator, output the first bit that the obfuscator, the output of the obfuscator. And that's a bit of information that you can compute given the obfuscation, and you cannot compute, given black box. So the obfuscator has to be randomized. There has to be a lot of randomization in it and kind of to garble the program well. Okay? Okay, good. So this led us to, like I said, to the conclusion that we should consider obfuscation with respect to auxiliary input. And I just want to mention that this idea of, considering auxiliary input is really not new, and it was done more than 20 years ago, or anyway, it was done a long time ago in the context of zero knowledge. So just to remind people who are familiar with this notion, so Goldwasser, Mikali, and Rakov defined the notion of zero knowledge in 85, and they didn't consider auxiliary input in their definition. And then a few years later, Goldreich and Oren came by and said, this definition is not robust enough. It can leak information. Again, if you kind of do it twice, and so you should consider zero knowledge with respect to auxiliary input. And by now, zero knowledge and zero knowledge with respect to auxiliary input are, one of the same. When you say zero knowledge, you mean usually with auxiliary input. So it seems like, the history is a little bit repeating. It's okay. So now we're doing it in the context of obfuscation. Okay. So that's the idea. Now let me give you. I'm not going to define exactly the definition of auxiliary because I think it's a little tedious. But if you want me to, I can do it. I have a slide here. But let me just give you the idea of obfuscation with respect to auxiliary input. So the definition is very similar to the original definition. Okay, whatever you can compute with a program, obfuscated program, you can compute with black box. But now we also consider auxiliary input. So now the adversaries also get some auxiliary information, Z, and the predicate may depend on Z. Okay? So whatever predicate, deterministic predicate, they can compute about the program. And Z, they can also compute with black box access to the program. And we distinguish, as I mentioned before, between two cases, where the Z is totally independent of the program P being obfuscated, and when Z may depend on the program being obfuscated. So we have independent auxiliary input and dependent auxiliary input. Okay? And, okay, so that's the idea. That's the, very loosely speaking, the way we define obfuscation with respect to auxiliary input. And so what we show is, we first show that there are many natural classes of functions that are not obfuscatable with respect to independent auxiliary input. Then we show that actually there are many more class of functions. If you allow dependent auxiliary input, you can have, we show many more class of functions that you cannot obfuscate. And on a positive note, I'm not going to talk about this during the talk, but I just want to mention it, that, okay, so now we defined auxiliary input, we kind of checked, what about the positive results? Do they still hold or not? And so what we showed is that any obfuscator for what we know how to obfuscate, so for password functions and for approximate password functions, is also actually an obfuscator with respect to independent auxiliary input. So if you allow independent auxiliary input, the obfuscator is still good. Okay? With respect to dependent, if you assume very strong assumptions, which I don't know if you need to call them assumptions because I'm not sure I believe them. So under, essentially maybe yes, maybe no, it's not clear. So, but anyway, for sure not any obfuscator. For the case of dependent, for sure there exist obfuscators which fail to obfuscate if you allow dependent, but maybe there exists, good obfuscators for dependent. This we're not really sure about. Okay, so this is our result. Like I said, I'm going to talk about the first two, and I think I'm going to mainly talk about the first because I think it's a more surprising result. And then if we have some time, I'm going to talk about the second as well. But let's start with the first. So we're talking about independent auxiliary input, and my goal is to convince you that there are natural classes of functions that are not obfuscatable. And what we show is that there are many filter functions which are not obfuscatable. And let me explain what a filter function is. So, yes, Guy.
Are they obfuscatable for the original definition?
Well, we don't know. With the original definition, we don't know about it. Yeah.
You don't know about any function that is?
So in the original definition, we know that only password functions and that's all. Yeah, very little. I mean, okay. I didn't mention it because it's kind of obvious and I didn't want to put too much noise into the talk, but every function that you can learn, I mean, very easy functions, you can obfuscate. I mean, functions that you can, given black box access, you can really learn the function, then, okay, there's nothing to hide. So you can obfuscate because nothing hidden is in there. But, so we're actually interested in functions that you hide. I mean, that there's some hidden secret that you want to hide inside your program. So within these functions, the only ones that you know how to obfuscate are password functions and approximate password functions. That's it. So what are these filter functions that we claim that we cannot obfuscate? And I think many filter functions. I'll explain what I mean in a second. But what are these filter functions? So filter functions, it takes as input a filter function is associated with some function f, and it computes this function for you only if you know a witness for x. Okay, so if you know some secret that's corresponding to x, it will output the function, but otherwise it won't. So it does some kind of filtering for you first. If you know the secrets that correspond to x, it will output, otherwise it will output, fail. Okay? And so let me give you some examples of natural filter functions. So there are several examples actually in cryptography. So let's go back to our example of signature delegation. Okay? So let's assume that Alice is willing to sign anything that Bob signed. So she really trusts Bob. She's like, well, if Bob signed the petition, I'll also sign the petition. Don't bug me, with all your petitions. Just, if Bob signed, I also want to sign. So what is she going to do? She's going to filter her signature function. Okay? So on input x, only if also you give the function Bob's signature, that will be the secret corresponding to x, only if you give Bob's signature on the message x, she will output her signature on the message x. Okay? So filter function is an example. So you can use filter functions to do signature delegation. Another example is that of a certification authority. So in cryptography, again, you want to make sure that the person user tells you this is my public key, but you want to make sure that it's a valid one. So sometimes the public key is a product of 2 primes. Okay, so here's my public key. You want to make sure that it's not a product of 3 primes, because then you may reveal secrets or something bad will happen. So usually what we do, there's some certification authority or a trusted center, and it authorizes your keys. So you give him your secret key and public key, he checks that it's valid, and he gives you some certification. Okay? So that's a certification, that's an example of a filter function. So you give him X will be your public key, the secret corresponding to it will be your secret key, and only if he checks that this is a valid pair, he will give you an authorization. Okay? So these are two examples of filter functions. And so let me give you a little bit more formally the definition. So formally, you take any class of functions f and any NP language L, and a filter function is we denote it by f sub L, and it's all the functions of the form that it takes two inputs, x and a witness for x being in the language, and it outputs f of x only if w is a valid witness for x being in the language. Okay, so these are filter functions. Okay, so each filter function is associated with a class of functions f in a language L, NP language. Okay, so now what is our result? Our result is the following. Oh, sorry, yes?
So if there's no witness, that the function delivers 0 or a null value or what?
Yeah, so if there's null or 0, yeah, just, yes, let's say null, okay? If W is not a valid witness. Yeah, so what is our theorem? We show that take L to be any NP complete language. Then we show that the filter class f sub L is not obfuscatable, where f can be any, let's say, encryption scheme or signature scheme or pseudo-random functions, and essentially f can be any unpredictable function. It needs to be very unpredictable. I don't want to go into the definition of this because it's kind of a mess, but you can think about it as any class of encryption, any class that has enough entropy, pseudo-entropy inside it.
Do you need complexity assumptions for that? P not equal NP or something?
Okay, so for our results to hold, we don't need any, and the theorem is true unconditionally. If P, now you can say, okay, if P equals NP, we didn't show anything interesting because it's kind of, okay, you didn't filter any, I mean, everything becomes trivial if you don't, I mean, if complexity, if crypto collapses, then this collapses, okay? If nothing, I mean, if there's no crypto, there's no crypto. But, so this result is interesting if, only if P is different, I mean, under a complexity assumption, but it's true unconditionally. I mean, the statement is true unconditionally. So,
Was this expected? I
that,
mean, that's kind of, so this looks like it's killing obfuscation.
right, so you're asking, isn't it expected that that's,
Well, was it or not? I have
So,
no idea.
okay, so
have people been trying to obfuscate?
Yes.
right, so,
Yes, people have been trying to.
Mario is full-time on obfuscating Microsoft code.
yeah,
I
so,
see, okay. Okay, so Mariusz, are you like gonna go hang your head someplace now or something?
No.
I know,
No,
I'm
so-
just kidding. But in other words, this is a little surprising then.
so I'm not, okay, so let me tell you, I'm not sure that this result is so surprising because actually, like when I started working on it, I was thinking probably this definition is too, probably you can't hide every single information that you want. That was my inclination. It's not, and that's what I'm going to try to get to later, but it's not true, it's not clear that you want to hide everything in the world that you want. I mean, maybe, so don't hide everything. So, or to say it's exactly the same as black box, so it won't be the same as black box, but it's almost the same as black box is also good enough. So I think that
That there are outs from this.
exactly. This result is not to say that the obfuscators that exist, you can actually, crack them and, crack the code and learn significant things. So that's the point. Okay, and
Is your result that shows that we cannot obfuscate, or is it specific that you know how to generate a cracker?
so yeah, so we okay, so
Or is
good.
it construct?
Okay, good. So
Does
here.
the cracker exist, or
Okay, so here's so here's the answer. So what are we going to show? What's the plan of the attack on the obfuscator? That's what. So the plan. So the attack is the following. What we're going to show. We're going to actually show that you can compute. It's not in existence. We're going to actually show how you can compute a piece of information from the obfuscator, from the obfuscation that you cannot compute given black box access, but assuming you're also given some auxiliary input, which is a totally random function in the family. So you're given also an obfuscation of G sub L, where G is totally random. Okay, so let's try to look into this more closely. So let's recall what F sub L and what G sub L are. So they take X and the witness, and they output the function only if X is a valid witness. Okay? Now, I'm going to show that given the two obfuscations, you can learn something that you cannot learn if the F sub L is replaced with a black box. Now, what is this assumption? What is this something that you can learn? I'm going to show that you can learn G of some X star. Okay? Now what is, so you can learn the value of G and some X star. What is X star? The intuition is that the witness for X star is some program that computes F sub L. Okay, so let's take so this is kind of a difficult part to follow. So again, so what's the idea of X star? Think of X star as the following statement. X star is the statement, there exists a short program that essentially behaves like F sub L. Okay? So what do we mean by like F sub L? Let's say there's this short program that on inputs xi and wi outputs f of xi. We'll think of f of xi and wi being, I don't know, the first, xi is the first t elements in the language. Okay? So essentially, X star, it should be thought of the statement there's a short program that behaves like F sub L, but you need to encode it in the language L. And here we use the fact that L is NP-complete. So the fact that it's complete, the completeness property says that essentially any statement with a short proof, you can encode in the NP-complete language. So if the NP-complete is graph 3 colorable, any NP statement, any statement that has a short proof, you can encode as a graph that is 3 colorable, and from the proof you can move to the coloring. Okay, that's the definition of NP completeness. So what we're going to so encode this statement that there exists a short program that behaves like F sub L, encode it in as a 3 colorable graph, or in the NP complete language L. Okay, now so that will be X star. Okay, now the idea is this: the adversary that has the obfuscation of F sub L, that's a short program that computes F sub L. So he has this witness, he converts it into the, encodes it in terms of the language L, feeds it into G sub L, and outputs G of X star. So whoever has this obfuscation, which is supposedly a witness, he can use it to compute G of X star. Okay. Now what about the poor adversary who only has black box access? Here we use the fact that F is unpredictable. Okay, so it's used in the following sense. If you have only black box access, you don't know a short program that computes F sub L. Okay, you can't, you can't shrink it or compress the program. You can't, because it's totally, it looks random to you. Okay, it's totally unpredictable, and therefore the person with black box, does not know a short program that computes or behaves like F sub L, and therefore that poor guy does not know a witness. Okay, so he does not know a witness, and therefore how can he compute this? G of X.
How useful is G of X star? What is G of X star telling you?
It's garbage. It's not useful. I don't think so. Again, I don't think the piece of information that I learned here is a useful piece of information. Okay, what the person learns is I don't think X star is valuable, and therefore I don't think G of X star is valuable. But nevertheless, you learned a bit of information that you wouldn't be able to learn with black box access. Okay, and so let me just so this is more or less the idea of the proof. Now I want to someone can say, okay, who cares? So two answers. First of all, on one hand, I agree, who cares? But that just says, okay, the definition is not good. Okay, because here, this definition, you can't achieve it, but. So this is one answer. Another answer is actually for cryptography, it's actually bad that you can learn something. Because in cryptography, you have your secret key and you really want to defend your secret key. Okay, and your secret key you're going to use, you're going to use it to encrypt messages and sign messages and so on. And if every time you obfuscate it, someone can learn something about it, it's kind of scary. And he can learn something, then he can learn something. You generate all these supposedly unuseful information about your secret key, but nevertheless it's your secret key and you don't want to run around and just spread information about it. So for cryptography, it's definitely if you want to construct like provably secure cryptography, this is kind of, it's kind of problem to do it.
But could you use it? I mean, so let's say each time you learn sort of one bit, does it really mean that then you wouldn't have to do a 128-bit attack, but only an 80-bit attack if you do it often enough?
I don't know. I mean, maybe. Look, at this point, you're asking me, if you do it many times, do you learn something, any useful information? I don't know. Maybe not. But maybe yes. And, it depends what else you give, what other... This is just an example. Maybe you can...
And that's what I wanted to ask you also. Do you get any idea from the proof that this is kind of the only failure mode?
Not at all.
Or not?
Not at all. Actually, I'm pretty sure you can get much more severe failures. And by the way, for the example, I'm going to get to your question in a second. In the example of dependent auxiliary input, we actually reveal the entire secret. So for the independent, we reveal some bit of information which may be insignificant. For the dependent, we show that actually you can really get the hardcore, the secret. I don't know if I'll get time to go into that, but yeah.
You seem to be critical on L being an infinite and unbounded language. So if you apply the model to, say, secret and public RSA keys, it look at it would break because this statement X star would be too long and would explode. It would not have room inside a secret or public key.
So you're right. First of all,
if you have 1024-bit
Yeah.
RSA, right, and this X star can be 30,000
you're right.
bits. And
No, you're right. Yeah. So what you're saying, well, G sub L and F sub L do not take the same input size.
Yeah.
So G sub L is a random function in the family, but its input size that it takes is much bigger than F sub L. Yeah, that's true. Yeah. So yeah. So that's the result about the independent case. So I don't think I have that. How should I stop here?
Oh, no. I'm certainly at least go until 11:30.
11:30. Okay.
If we start
Okay.
late and we ask a lot of questions.
Yeah,
Okay.
we've been asking lots.
Yeah, okay, no problem. Okay, great. So I'll do it until... Okay, so I do have some few minutes to talk about the dependent auxiliary input case then. So let's now move to the dependent. Unless, is there any more question about the independent case? Okay, so let's move to the dependent case. So what can we show about the dependent case? Here we have a conditional result. Okay, it's a little weird. But what we show is, we can show that either many point filter functions cannot be obfuscated, and I'll explain what a point filter function is, or essentially most of the things you want to obfuscate, you cannot obfuscate. So you cannot obfuscate encryption functions, decryption functions, signing functions, pseudorandom functions, and essentially you cannot obfuscate anything that's sufficiently unpredictable. Okay? So either you cannot obfuscate point filter functions or you cannot obfuscate almost anything else. That's the, very loosely speaking, the theorem. Let me first...
Is that an exclusive or?
No, it's not exclusive or. Sorry, so I shouldn't say either or, because either is exclusive, right? So this or, it's not exclusive or. You may not be able to obfuscate both. Okay. So let's start. So let me start by saying what a point filter function is. So a point filter function is a type of an access control function. Okay. So it has some statement associated with it and a secret, and a secret bit B, and it outputs the secret only if you know some witness corresponding to the secret. That is corresponding to X. So if you know some secret about the statement, it will give you the B. Okay? So if you think of W as some access. Okay? If you are allowed access, you get the secret. So let me give you an example of a natural point filter function. So for example, I'm going to reveal my phone number only to people who have some signed email from me. So only to people that I sent an email, I'm going to give them my phone number. So the statement, so the bit is my phone number, or the first digit of my phone number, whatever, and a witness will be a signed email.
What is X?
The statement is, do you have do you have a short signature of mine? It's not really a statement because Okay, so let me give the formal definition. And so the formal definition, you have an NP language, L, and you define delta sub L, the class of point filter functions that relate to L. So for any x and any b, there is a point filter function. And the point filter takes a witness for x being in the language. So you can think about x, now going back to this example, you can think about x as being my public key, and a witness for my public key is a signed message, a signed email. Okay, so that's an example. So the class of point filter functions take a witness for x, and if it's a valid witness, it outputs the secret, otherwise, no. Okay? So this is an example of point filter functions, and let me give now the theorem. So the theorem for the dependent case, we show that there exists so we show that the point filter class, delta sub L, is not obfuscatable for any NP complete language L. It should be complete, like before. Or, essentially, anything unpredictable is not obfuscatable. Okay? And there's another formulation, an equivalent formulation of this theorem, that says if you can obfuscate delta sub L for one NP complete language, then you cannot obfuscate any unpredictable function. Okay? So now it's like, so you know, when we prove this theory, we're like, okay, we really want to show that you can obfuscate delta sub for some L. You know, so find some L that you can obfuscate it, and then so I think that's a very interesting. It's kind of an interesting question. Can you obfuscate delta sub L for some NP complete language L? And we don't know the answer. I mean, sometimes there were times we thought, oh, you can't, and we said, can't. We ran back and forth, and now I'm all confused about this question.
Could you repeat this statement?
Yeah. So what we show is we show that if there exists some NP complete language for which delta sub L is obfuscatable. So if you can obfuscate delta sub L for some NP complete language L, then you cannot obfuscate almost anything else. In other words, you cannot obfuscate any unpredictable function, any function with enough pseudoentropy in it. You cannot obfuscate any function that's incompressible, that you can't compress, essentially. That's the idea. So that's the theorem.
And you're not sure what you believe. I mean,
Yeah, I really, I don't know. I really don't know.
So this, unfortunately, now is not constructive.
No, actually, it is constructive. So, okay, so what's the plan of the attack?
Use this thing that you.
So what?
Right.
So you take
She's
one of
going to
these.
use the one that you can obfuscate.
No, but
to
let me
construct
also, you
this
just
for
take
some
one of
reason.
these encrypted functions.
Exactly.
Just try it, and if it's true, then you will be successful.
Exactly. And so, actually, the proof of this theorem is actually much easier than the proof of the previous theorem. And the plan of the attack, the way we're going to prove it, is we're going to show that you take any function class F that's unpredictable, okay, and any NP complete language L. What we're going to show is that you can compute something from the obfuscation of F that you could not compute from black box, given auxiliary input, which is an obfuscation of the point filter function delta sub L with some x star and b. But the question is, what is this x star and b? Okay, so I'm giving you this piece of information. Okay, so let's just recall what the point filter function is. The point filter function that's associated with x star and b, it takes some witness w star of x star and outputs the secret good b if it's a valid witness, right? That's okay. Now what's going to be the x star and b? So b is just a random secret bit. Okay, so it's just a random secret. What is x star? X star here will be weird. Okay, here's where in the dependent case, the contrivedness in some sense comes in the auxiliary input. Okay, so the x star is weird. What is x star? X star will essentially say, as before, it will essentially so consider the statement: there exists a short program that behaves like F. Okay, so in other words, okay, what do we mean behave like F? So there is a program that.
You don't want to have witnesses in it. This has to
Right. Sorry, I have here. I'm sorry. This should be and it shouldn't be x1, it's 1 until t. Sorry, this typo in the slide. I'm sorry about this. So now, right, so f doesn't have a secret into it, okay? So the question, so consider this statement, there exists a short program that essentially computes f, okay? Or agrees with f, let's say, on inputs 1 till t. Okay, now the idea is the following. Now, take this statement and encode it in your NP-complete language. So encode it as a three-colorable graph. Okay, again, you can do it because the language is NP-complete. So again, we're strongly using the completeness of the language. And now, good. Now the idea is the following. The witness of x star will essentially be a short program that computes f, okay, or translated into the language, into L. So if you have an obfuscation, that's a short program that computes L, and therefore you can feed it. From obfuscation of f, you can essentially get W star, compute W star, and therefore find the secret bit B. On the other hand, if you only have black box access, you cannot compute the secret bit B. And again, here we're using the fact that f is unpredictable. So if you have only black box access to f, you cannot compress it because it's so unpredictable. You can't find a short program that computes f or agrees with f on inputs 1 to t, and therefore you do not have a witness W star, and therefore you cannot compute the secret bit B. And the reason you cannot compute the secret B is because this is obfuscated. So we're using the fact that the auxiliary is obfuscated. So that's more or less the idea.
Now you said you can learn the whole secret.
Yeah, so the entire B. You can put here any secret, okay? So my point is, what you learn here is not contrived. It's actually the secret that's associated with the point filter function.
So what's contrived is the auxiliary information, but
Essentially,
the secret is
exactly.
But what you're learning
Yeah,
is the disaster.
Exactly. So this let me conclude because this.
So can you find such weird auxiliary information? You say the auxiliary information is contrived. So if I'm trying to destroy your system, how hard is it to get this auxiliary information?
So that's okay. So I'm not saying at all that it's easy. Maybe it's impossible to get the auxiliary information. The only point. So my main point is, look. Amazing obfuscator, like you want to achieve like black box access, forget about it. Okay, that probably. I mean, we didn't show it for every class, but it seems like they're very natural classes that you cannot obfuscate. So probably the definition is too strong. Now, one may say, okay, so when you look at the first example, you say, okay, so just you say you learn something meaningful, but no, you can't. Even if you learn something meaningful, you have counterexamples. But then say, okay, the auxiliary information maybe is not so interesting. Consider, no, but even if you have auxiliary information that's actually just a random function from the class, that's very normal. Even then, you could. So I think the point is, I think one of the main point that at least I want to continue working on, to try to come up with a good definition, okay, that still captures, or maybe it doesn't exist, but does there exist a relaxed definition that really captures the notion of obfuscation that you can achieve, okay? That's one thing. Another way is maybe try to relax the model in any way. So there are several ways to go about that. A way that I think some people talked about, but I'm not sure if I don't think anybody. I'm not sure if it was really carried out. But maybe try to take some small hardware device it's black box, really small device, and put that in the program. Now can you obfuscate it, given that small device? So there exist some devices that you can, but maybe they're too big of a.
So you say use dice words or something.
What?
Dice.
Yeah, exactly. Yeah. So that's it.
Thank you.
Okay.
Is there any known relation between this kind of definition, hardness of learning the program, and hardness of modifying the program? For example, if I do the password checking to prevent anti-piracy,
Right.
sometimes it's okay for me if a small change to bypass the password checker just propagates to so many places that the whole program is degraded after the change.
You're right. I don't think this works. Yeah, I don't know. It's a good question. I didn't think about that question. It's a good question. So you're right. So you're saying the definition of the definition as is all. It's not strong in a totally different dimension. Maybe you can change the program a little bit, and
Usually all we want is to make it useless to make small changes in our programs. I don't care if you understand a lot of the program, but once you do a change, we can do so many cross checkings. Many other places will deter you that that's what we do.
I see. It's a good point. I don't think I need to think. Yeah, we didn't consider it when we worked on this problem, and I don't think it was considered by the previous work. But I need to think about that. It's a good point. Thanks. Yeah. Oh, sorry.
I came late and I want to watch the slides. In your list of reasons to obfuscate, you seem to have omitted the famous instant job security. People make sure they can't be fired because only they understand their code.
Oh.
And I suspect there must be an incredible harvest of oral history in the year 2000 conversion project, because they had to dig stuff by people who left 7 layoffs ago. And you can get how friendly they are about telling you what they've done.
Oh, and that Gideon remark. Are there any other questions? Okay. So what slide
Thanks.
now?